We are the team Aerospace Peru of the Smart Machines Laboratory of the Technology of the National University of Engineering in Lima, Peru. And in this Latin America Space Challenge, we come with the Kuntur Project in the category of solid propellant rockets of 1 kilometer, from the Andes to the stars. Our team focuses on the study of the technical pillars for the development of manned and unmanned spacecraft. In the mechanical part, we detail the aerodynamic study and design, selection of composite materials, especially carbon fiber. In the avionics, it details the embedded system for sensor measurement, ejection and recovery system, telemetry and payload. In the propulsion part, the calculation of the appropriate rocket motor for the mission is detailed. In the interface part, the data is sent to a ground monitoring device. All this in a formative approach with new technology in Peru. The present slide details the parts and the segment of the rocket, a von Karman warhead, the recovery system and payload in the larger diameter cylinder, the recovery mechanism, the telemetry and avionics in the smaller diameter intermediate part, and the propulsion system with three fins in the intermediate length diameter at the end. The rocket has variable diameter to reduce weight. Hyperlike, the rocket has four materials that integrate all its construction. Carbon fiber in 80% of its the entire structure, in the fins and cylinders. Fiberglass for the telemetry section and the bone carbon ogive. Aluminum as a skeleton in the rings and bottom for the location of the engine. 3D printing for the encapsulation of the payload and the isolation of the motor. The system in general is detailed below, showing the engine part of a Pro 54, the commercial electronic system to measure the experiences of fin deformation, kinem- kinematic viscosity in flight by pressure differences tube, and the general kinematics of flight. The expulsion of the payload for the sensing and interaction of the biological load, consisting of bacteria from the Peruvian Andes capable of generating changes of state in the water, achieving micro-precipitation or micro-dripping. We can see on the right side the composition of the payload called Kinti, its electronic system, the geometry, and the recovery system by deceleration rotor. This experience and future approach can be applied to counteract floods that generate heavy economic losses at the civil and industrial level in the north of Peru. For this reason, we won the Innovation Prize in Peru in 2018, awarded by the Society of Mining, Petroleum and Energy of Peru. The geometrical dimensions of the rocket are then established from the weight of the rocket along the center of mass from the base, the total length, and the reference diameter, which is usually the largest. As variable diameters have been chosen, there are reductions that must be considered for their effect. Finally, three rings are considered with the dimensions shown in the table below. According to the stability calculations, where the flight lift coefficient is comparing a stability diagram according to the diameter reference, the following parameters observed in the table with respect to the lift, torque, and fineness have been established. Now we will see the propulsion system chosen, being a solid full-engine Pro 54 of sorbitol composition. These are the geometrical measures. The following specifies the physical and energy values provided by the engine, such as total weight, propellant mass, which is approximately 1 kilogram, gravity input, maximum thrust, average thrust, burn duration, total impulse, etc. At the same time, the transient thrust curve and points parameters for trajectory simulation. Before that, to observe the trajectory of the system including kinematics, it is necessary to know the dimensions of the parachute, which, uh, which are shown and sort their system at higher velocities. After that, the surface area of the parachute is considered in addition to the characteristics of the launching system, a launching length of 4 meters, a specific angle. In addition, to establish the trajectory, it is necessary to take into account the starting mass, the wind speed, which is 5 meters per second orthogonal to the flight direction, etc. The calculations are run and you have this trajectory. It is compared with the Eiffel Tower on the detailed XY and Z curve. After that, the comparative of the launch and landing are established in a kinematic way, establishing maximum values in velocity, acceleration, and height as shown in the following figure. The force versus time curve is shown below, comparing thrust, weight, and drag force. Acceleration versus time curve, longitudinal acceleration, and other two-sense panorama are shown below. The speed versus time curve is shown below. The position versus time curve at range and altitude is shown below. We can conclude that the proposed flight according to the design and variable diameter of the rocket is stable. Kuntur has an airframe length of 2,390 mm, airframe maximum diameter of 143 mm, and a lift-off mass of 7.3 kilograms. According to the flight prediction, we can conclude that it will have a lift-off thrust-weight ratio of 12.46, a launch rate deploy velocity of 25.5, a minimum static margin during boost of 4.42 x referential diameter, a maximum acceleration of 89.7 meters per second squared, which is equivalent to 9.14 g, a maximum velocity of 175 meters per second, and a predicted apogee of 1,152 meters. The parachute fall deceleration is 8 meters per second, and it will have a main deploying altitude of 1,150 meters. Thank you very much for your attention and opportunity to explore our work. Follow us on our social networks as Aerospace Peru, from the Andes to the stars.